A, B, C, and D are 4 points on the circumference of a circle.
Mhm.
Oh, I didn't quite. Yes, it only just fitted in. Right, fine. A, E, C, and B, E, D are straight lines. Well, we probably assumed they were, didn't we? So you see how they're using, it's a bit, it's not explained, but you can see how A, E, C, they're just reassuring us really that what we thought was a straight line there is indeed a straight line going through 3 points A, C, A, E, and C. And the same for B, E, and D.
Yeah.
So big deal, those are straight lines, and so are these, presumably.
Yeah.
Prove that triangle ABE and triangle DCE are similar. What does that word mean in maths?
Similar. I don't know. In maths, I'm not sure.
Exactly the same what?
Oh, the same angles? No, area?
Yes, they will have exactly matching angles. Not area necessarily, although they might do. If they've got exactly the same angles and also ratios. The short way of saying that, although let's put angles as well, because that's a good point. Exactly the same angles is a good point. And ratios. So there'll be all sorts of ways of matching the ratios. Let's see how they might match. The point is that the ratio of this length, you see the two triangles we're talking about.
Yeah.
ABE and DCE. ABE, this triangle here, and DCE is this triangle here. Now they do look like they probably have got roughly the same area, don't they? Which is interesting. So, but you have to, if they did and they were similar, then I think these lines here would have to, the quadrilateral here would have to be a rectangle, I think. No, that's not true. But it would have to be kind of isosceles as not a trapezium necessarily. It wouldn't need any parallels, no. Whew. I'm not sure whether there would need to be a pair of parallel lines. That's an interesting mathematical question. But we'll put that to one side. But you see the two triangles we're talking about. What could be the matching ratios? Well, it might be that the ratio of this side to that side, so BE to BA would be equal to what ratio on the other triangle?
BE to BA. DE to DC?
I don't think so, no. I doubt it.
CE.
It would have to be CE.
Yeah. To CD.
To CD, yes. Yes, exactly like that. See how it's crucial to pick a correspondence carefully.
Yeah.
But there will be dozens of ways to do that, only slightly exaggerating. Might go into a dozen or more. Where you can see that there are matching ratios on a result of the similarity. And then the angles will all match as well. Which angle do we think is going to match with that angle? And match in the sense of just being equal?
CB?
Be the same as which one?
CB? Oh, no, wait.
Now you'll need 3 letters to define an angle.
Oh, okay.
This angle here would be ABE.
The
same name as the name of this triangle.
Oh, yeah.
But if we put an angle sign before it and said angle ABE, people would know that we meant this angle and not the whole triangle.
Yeah, okay. So I think it would be the same as DCE.
Yes, so do I.
Okay.
Right. And by the way, that's kind of key to this problem. Showing that the two triangles are similar, we're going to do that by showing that they do have matching angles, that these angles are equal perhaps. So we'll be looking for a way of showing that we know that's true without knowing that the triangles are similar. You see?
Yeah.
That'll be, you know, the reasons at each stage of our working that we're giving. We'll be finding out that we'll be showing how we know these angles are the same. And then if we can show that all the angles match, so actually, which angle is this matching with?
That would be AEB.
Yes.
Is that how you'd say it?
I was too lazy to call this DEC, but you called that AEB exactly. And you can see exactly the reason why those two angles are going to be equal, of course, can't you? You know the name of that reason.
Oh, I can't remember. Is it like the corresponding out things?
Much simpler, really. It's just saying relative to this vertex, these two angles are on opposite sides of it. So the whole phrase is vertically opposite, but opposite will always do. Nearly always. But they might refer to two angles as being vertically opposite. So you have to know that the vertically there has nothing to do with vertical and horizontal. Okay, it's just a big word for this, you know, easy sense of how they're opposite, vertically opposite. So we're well on our way. You know, we probably will go about showing that these are similar by showing that this angle matches there. And then we'll think of a reason why we know that these are matching, which you probably can straight away.
Because they're right. I don't know how to word it really.
We'll talk about that in a sec. But let's just say, let's just sort of stay zoomed out for a minute and notice that, yes, if all of the angles match, so if these two match, and then these two match, and then these two match, which we suspect they will as well, don't we?
Yeah.
Then we've proved it.
Okay.
All we've got to do is find reasons why these two match and these two match. But then we haven't mentioned ratios at all, and we don't have to.
Okay.
So triangles are similar, or any shapes indeed are similar. Any shape, no matter how complicated, that's going to be similar to this one.
Yeah.
Roughly. If all of these angles, you know, that angle coincides with that one.
Yeah.
You know, even this angle and that angle, which I haven't drawn very well, but you get the idea.
Yeah.
But if that's true, if all the angles correspond, then we'll find that all the ratios correspond as well.
Yeah.
So exactly the same angles and ratios, but you only, you know, what you can do, and here's where this topic gets a bit awful and I hate it, is when we use a bit from each, angles and ratios. No, I don't hate that in principle. There's just one particular little rule, which I don't think should be a rule. Anyway, exactly the same angles and ratios. What's you know, basically the same what?
Same.
These two things are the same
scale. Well, no, not the same scale.
Not the same scale. That's right. They're not the same size, but they are the same.
I know that it's. I can't think of the word.
I probably used it already, haven't I? Accidentally. So you didn't mean that.
Oh, okay. They're the same rate. Well, no, they're not. They're I don't know.
The ratio, by the way, another good word for ratio is, what are other words for ratio? Have you heard this one? Proportion.
Yeah.
And that is, you know, useful because outside of maths as well.
Yeah.
Well, you would say that everything is in the same proportions here. And you
yeah.
mathematical sense of proportion or ratio. Another word is fraction. And then I think I'm forgetting another, because after all, we could have written these facts like BE over BA. If we're going to put an equal sign between ratios, we probably prefer to turn them into fractions. It's not bad to put ratio equals ratio. It's more common to convert them into fractions because fractions are basically ratios.
Yeah.
Sure, there's another word I'm forgetting for the same thing. Quotient.
Oh, yes,
you won't come across that one in GCSE much, but it's just a slightly more old-fashioned word for a fraction, or proportion, or ratio. Right. Okay. So not necessarily the same size, but the same. This other word, which
proportion.
Sorry.
The same proportions.
True, but the much simpler word.
The same shape.
Exactly. Yes.
Different. Oh,
yes,
okay.
The point is, all of this really is about defining the shape of something. If we say two shapes are similar, then we mean they are exactly the same shape, but not necessarily the same size. And then we've got another important word which you need to know. So that's exactly the same shape. And then we've got another important technical term if they're not only the same shape, but the same size. Oh my God, it's 7:10. But then what happened?
It's all right.
It's partly for a bad reason.
It's fine.
It's ages confusing you with this bar chart. And I think that was my confusion. But anyway, right. Anyway, so similar means exactly the same shape. If it's also the same size, then the word is similar plus same scale, as you put it. And then you thought, well, no, not the same scale. But you were thinking there is a scale. That's right. If they're similar, then there will be a scale factor of enlargement.
Yeah, that's what I was thinking of.
I know. Yeah, that's why you're saying scale. One scales up or down to the other one. So similar plus same size. The important technical term is begins with C.
Is
N G.
Congruent.
Yeah. But this isn't proving that they're congruent, because they might not be. And I was just wondering if they were, would they have to have any parallel lines here? I still haven't worked that out. Still confused about that. All we have to do here, though, is show that all these angles are the same.
Okay.
Now, so we've shown that those are the same because they are, what did we say?
They're opposite. Well, vertically opposite or something.
Good. Yeah. Now these are the same for a reason that I'd prefer to take 5 minutes to discuss.
That's fine.
But so we'll leave it till next time. But you just quickly, you might recognize it if I draw it like this. Circle. So if we remove two of the lines, if we go from A to B and from D, and then you think of that angle there, and now imagine allowing this point B to migrate along the circumference. But these stay straight. Perhaps they're elastic, very tight elastic bands, so they're straight.
Yeah.
So if these stay where they are, A and D, but B starts moving.
Mm-hmm.
Can you imagine that happening?
I could not, but
okay.
I guess, yeah.
Let's not hurry that. Let's discuss that. Hey, and I wonder whether, you know, yeah. Okay, so we'll look at that next time.
Okay.
So we'll pick up with that next time. How B is migrating and what happens to the angle there.
Okay.
So what do we have to do? Show that these two triangles are similar. Mm-hmm. And we showed that these two angles, we talked about the fact that angles match. Sorry, the triangles are similar, that's right. We talked about the fact that shapes are similar, in other words, the same size and shape. I take that back. If they're the same size as well, they're congruent. Shapes are similar, in other words, congruent, but not necessarily the same. No. In other words, they're the same shape, but not necessarily the same size. So like these, one is an enlargement of the other, not necessarily with a scale factor of 1. Then they're similar in the mathematical sense. And shapes are similar when all of their corresponding angles match. Corresponding in the loose sense of you can find matching pairs.
Yeah.
And what I said I'd better leave for a 5 or 10 minutes discussion, although that's probably over-egging it, is an explanation of why these two angles match here, and indeed these two here. At which point we're done. And as circles problems go, it isn't necessarily I can't remember how many marks it was, but so there's not that much to it, because we can just do it with the angles. So how can we show that these two angles are equal? What I didn't realize I could have done last time, although I'm not sure how well you'll see this, because these, what I'm doing there is really for another purpose. It's not for showing stuff. It's for drawing stuff, right? But can you see the bit?
Oh yeah, yeah.
There. So you can see how that's equal to the angle at C.
Yeah, yeah.
Now it's joined by two straight lines, right? To A and D.
Yeah. Yeah.
So it's like those are tight elastic bands. So if I move the join of them to B, it must be the same as that angle too, mustn't it?
Oh yeah, yeah.
But has it changed?
No.
Not if you can believe me that this angle is equal to that angle.
Yeah.
But we can't just say that. It says here, you must give reasons for each stage of your working. I mean, for these two angles here, we were able to say they're opposite, weren't we? Opposite angles. But why should we be able to state that this angle is the same as that angle?
Wait, are you asking me?
Kind of. Not. I mean, I'm ready to tell you, but I just don't want to tell you if you do know.
I don't.
No, just sort of make sure. Because otherwise, some people are just too polite to stop me yapping on, you know. So do stop me at any time. And the reason is, I mean, I'm not sure if you'll accept the reason. You might say, I thought you were going to explain this to me, and all I'm doing is saying it's a rule. What they expect as a reason is for you to just quote the rule that angles on the same segment, angles in the same segment, and I'll explain what that means in a minute, are always equal. So not only are C and B equal, but all along here, look, you can probably see it's believable, isn't it, that the angle isn't changing at all. no matter how close we get to A, we've still got the same angle. What is it, roughly, would you estimate, that angle?
25 degrees? No. A bit less, like 20 degrees-ish.
Oh, I think it's, I think it's quite a bit more than that, because to me, it looks like more than half of a right angle.
Oh, wait.
I'm talking about the angle here.
Oh, right, okay. Oh, okay, yeah.
Which, after all, we are saying is the same as these.
Yeah.
Don't you think that's more than half a right angle?
Yeah, I do. So, probably... I don't know.
How many degrees is half a right angle?
Half a right angle?
Yes.
Oh. 40. I know a right angle is 90 degrees. So,
yes.
like,
and well,
half
then.
of 90, right?
Yes. In other words?
What? 45.
Yes. 45 degrees is a very important angle because it's half a right angle. Do you have set squares in your pencil case?
Yeah.
These plastic triangles?
Yeah.
And one of them is roughly that shape, isn't it? And very often it's got a smaller one, which gives it its look. Piece of plastic with a similar triangle, similar in the mathematical sense, exactly the same shape triangle, but just smaller, cut out a bit in the middle. Do you recognise that piece of maths equipment? Yeah?
Yeah.
And then there's another one with a slightly different proportions. More like that, isn't there?
Mm-hmm.
What are the angles in these two set squares?
90 degrees.
Absolutely, here and here. That's right.
Yeah.
Here, they've both got a right angle. And of course, why are they called set squares? For setting lines square with each other.
Mm-hmm.
Square in what sense?
Wow.
If you set two lines square with each other, what do you probably mean? I mean, you know, it's not. If we say, oh, let's set this line square with that line, we probably mean like that, don't we?
Okay, yeah.
In other words, making a square corner.
Okay.
Well, I mean, the symbol would be a little square in the corner, wouldn't it?
Yeah.
Why is that? Why do we use a little square in the corner to represent 90 degrees?
Ooh. I don't know why it's a square, but I just know that's what you do.
Okay. But what do the corners of a square look like?
A triangle.
Do they? Oh, I see what you mean. Here's a square. So you could say, in a way, there's a corner of a square, and I've just made a triangle. Is that the kind of thing you mean?
Yeah, that's what I meant.
Maybe. There's a corner of a square. Yes, true. But the corner of a square makes an angle. It's where two lines meet. And what angle do they make?
Right angle.
Yes. And I'm just guessing. I might be making this up, but I'm just guessing that that's why we draw a little square.
Oh, okay.
To mean a right angle. Because it is, after all, a little square that you're drawing there, which has got all right angles.
Yeah.
Seems fair enough, doesn't it?
Mm-hmm.
But I am making it up. It might not be true. Who knows? Right. But I'm just talking about the meaning of the word square as in set square. When you set one line square with another, you do mean that you are setting them at right angles.
Okay.
And so that's one use of a set square, for drawing a straight line down there, and then bringing your set square up to the straight line, and drawing another line there, which is square with it, or at right angles. So I don't know whether you've ever bothered using either of these for that purpose, to draw right angles. Have you?
Not really, no.
I mean, it's a shame, isn't it? Because drawing right angles is something you often want to do, isn't it?
Yeah.
Yeah. If you're drawing a graph or something.
Yeah.
But don't leave these poor things unused. Let's remember they're there, but not just for that, not just for their right angles, not just for setting things square with each other. They both do that, but they're also useful for drawing some other special angles, like what? What special angle is this one probably good for?
What special angle?
Yeah, I'm thinking of this one here. What angle is that?
What angle is that? I don't know.
It would be easier if you had the set square there to actually play with, and if you had two of them,
yeah,
you could put them together like that.
Yes.
Making what shape?
Making a square.
Yes. So now can you tell me what this angle is?
45 degrees.
Yes, indeed. So you know this as your 45 set square, because apart from a right angle, it's also got a 45-degree angle here. What's this angle here going to be?
45?
45 as well. It's isosceles, isn't it?
Yeah.
So that's the special right angle triangle, which is isosceles.
Yes.
And 45 here and here. What about this one? What about this set square? What angles has it got apart from a right angle there? Can you guess?
Probably like 15, 17. Oh, 45. I don't know. Like 17? No, 17 degrees-ish.
Did you say 17?
Yeah.
Or 70?
No, not 70. 17.
So which one? This one or this one?
Wait. Well. Oh wait. Oh, would they be different angles?
Here and here. Otherwise, it would be that set square, wouldn't it?
Yeah.
How many set squares have you got?
2.
Yes. Just this one, which is the isosceles, and it's symmetrical about that mirror line, isn't it?
Yeah.
But this one isn't symmetrical about any mirror line, is it?
No.
It's got rotational symmetry. No, it hasn't. What am I talking about? Well, it has. Everything's got rotational symmetry. Sorry, I wasn't overdoing the... I did make a genuine mistake there and correct myself. I said, no, it hasn't got rotational symmetry. Oh, yes, it has. That was a genuine mistake. Because everything's got rotational symmetry of at least order what? Have you heard about rotational symmetry? Order of?
No.
So this odd shape here, even, that'll have rotational symmetry of order 1. The meaning of that is that on one full rotation, if you were to fix it there with a needle, okay, you with the needle of your compass, you fix it there, and then you start rotating the whole shape round. On a full rotation, the order of rotational symmetry is how many times it lies on its own pattern. And it'll have to go all the way round to get back on its own pattern.
Okay. So like, what would a circle be?
Oh, good example. That's a bit difficult. Let's come back to that in a second. What would a square be? What would the order of rotational symmetry of a square be? How many times would it sit on its own pattern on a journey all the way round?
3 times?
But you're allowed to include the one you eventually get to or the one you started at, but not both for some strange reason. Which is why we say any shape at all has got rotational symmetry of order 1. But we don't say 2. You might say, okay, it's already sitting on its own pattern, and then when you take it all the way round, it's sitting on its own pattern again.
Yeah.
But we don't. You know, you've got to make decisions about this, and the convention is that's order 1 because once, just all the way around, but not where it started. Or where it started and not all the way around, okay? But that means a square has got rotational symmetry of order
4.
4 in all, yes. Now, some triangles have got rotational symmetry of order what? Well, they've all got rotational symmetry of at least order 1, right?
Mm-hmm.
Some triangles have got a bigger rotational symmetry of, I guess not 2. I can't think of a triangle with rotation. I'm just trying to check. Don't think so. But what kind of triangle might have rotational symmetry of order 3?
An equilateral?
Well done. Exactly. Well done. Yes, you did the necessary thinking there. To think, oh yes, that might do the trick. If I held it steady in the middle there, it's going to sit on its own pattern 3 times. You get tested on this in GCSE, knowing that language of rotational symmetry, as well as the more familiar kinds like, like what kind of symmetry do you probably know about?
It's like reflections, I guess.
Exactly. Yes. Reflective symmetry.
Okay.
Quite. Where was I? So these triangles here, even this one hasn't got rotational symmetry of order 2, only the whole square. And as long as it's a plane square without all the detail there, you could say the square's got rotational symmetry of order 4. What about a rectangle that's not a square? What would be the order of rotational symmetry of a rectangle?
Would it be 2?
Yes, well done. What about a parallelogram? Whoops.
Would that one be 2 again?
2 again, well done. Can you actually visualize the rotation?
Yes.
I'm guessing you probably did.
Yeah, I did.
Good. So you can see how halfway round it's going to be lying on its own pattern again. Good.
Mm-hmm.
Has it got any mirror symmetry? A parallelogram?
Yes.
Tempting to think so. You know, why shouldn't a mirror line be going down like that?
Oh, right, yes.
But when you follow it through, you see, no, it doesn't quite work, does it?
Mm-hmm.
Even setting the mirror line this way and that, it just doesn't work.
Mm-hmm.
Okay. Now, what are the angles here in this set square? What are the angles in this one again?
Oh, in that one, it was 45 and 90.
And
45.
And 45 again. Good. So that's your 45 set square. What should we call this? Well, the angles are different.
Yeah.
Otherwise, it would be isosceles like that one. And if this was 90, and these are and the other 2 angles are both the same, then they have to be both 45, don't they? Because they've both got to add up to what?
180.
Okay, which angles add up to 180?
Oh my gosh, that is a... Wait, isn't a triangle 160, I think? No.
No, you're right, it's 100.
Wait, so...
But the thing is, all 3 angles have to add up to 180, don't they?
Oh, right, okay. Yeah.
So in a right-angled triangle, it's worth noticing that the remaining 2 angles, apart from the right angle, must add up to what?
Mm-hmm. Oh, 90.
Yes. For example, 45 and 45, if they're equal.
Yeah.
But here they're not equal, although they are going to add up to 90.
Yeah.
Now,
so...
they are kind of special, just like 45 is special because it's like half of a right angle. Hence, you get this nice symmetry here. Reflective symmetry. But as I say, this other set square has got no reflective symmetry. It's only got rotational symmetry of order 1, which is no more than these very asymmetrical or non-symmetrical looking shapes. But how can we see, well, why did they choose these? What's special about these two angles? What it is if we were to, here we got a square when we doubled it up like that, didn't we? Are we going to get a square? My picture isn't very good here, so I hope you can think of the actual familiar plastic triangles that you're used to probably ignoring in your pencil case. But you've seen them often enough to hopefully see, you know, imagine that you're actually playing with them on a desk, yes?
Yeah.
You're familiar with that shape, yeah?
Yeah, yeah.
So if you had two of them together, and then they would make that rectangle there, but it wouldn't be a square, would it?
No.
So it's not like we can say, we can see what fraction this is of that. I mean, we can't.
No.
But if we were to take two of them together and put them next to each other like this, we would get something special. Can you see what we get?
Yeah.
What?
And is that an isosceles? I can't really tell, but...
This one here? Well, it is isosceles, yes, but it's even more special than that.
You get another triangle.
Well, yeah. Anything special about it, despite my poor drawing? Diagram not accurately drawn?
I don't know.
Okay, it's my drawing. Sorry, it's terrible.
Okay,
but this is meant. Can you believe that that would look exactly like this?
Oh. Okay, so it turns into an equilateral triangle.
Got two of them back to back. Yes.
Okay.
So what are the angles here?
Oh.
And then, well, let's do this one first. What must this angle be? Which is like this one, or this one, or this one, because they're all the same, aren't they, in an equilateral triangle?
Yeah. Okay, so 60 degrees.
Yes. Whereas this one then will be
60. Oh, that will be 30.
Yeah.
Oh, well, that help. Yeah.
Yeah, you were going to add?
I know, I was going to say that one that you were drawing.
Yeah. 30, because it's going to, these two have to add up to 90. That's one reason.
Oh, right.
What's the reason this would be 30?
Because it's... I don't... Oh, because 60 and 30 add up to 90. So...
Well, that's one reason. What's the other reason?
Oh.
Which I think... Because I don't think you used that, did you? Or did you? Did you make them add up to 90 and choose 30, yeah? What was your reason for choosing 30?
I thought of all the angles in the equilateral and then half to 60. Oh.
Oh, hang on though. Yeah? Say again. All the angles in the equilateral are 60.
Yeah.
So
yeah.
On that basis, how do we get from there to this being 30?
Just half 60.
Yes, and we're cutting one of those angles in half, aren't we?
Yeah.
That is what you meant.
Yeah, yeah.
Yeah, great. Yeah, that's what I was trying to get at. Yeah.
Okay.
Yeah. Use that as well. But notice also they add up to 90, as we were also saying.
Mm-hmm.
When you're doing geometry, all sorts of different reasons appear at you from this way and that. And you can pick any of them. Right, so this is your 60-30 set square. And this is your 45 set square.
Okay.
So it's useful to start recognizing these angles. 45 degrees is half of a right angle. So you look at an angle like this and you think, oh, is that more or less than half a right angle? So if I imagine a complete right angle with that, oh yes, this is opening up more than halfway of a right angle, isn't it?
Yeah.
So This angle, what would you guess it probably is?
So I don't. Wait. Can
you see what I mean about trying to judge whether it's more or less than
a
right angle?
Yeah, but I just can't guess the angles. I can see it's more. So like
you see, what I would ask you to do, if I could, was get a ruler and try to draw a 45 degrees from, say, this side, and it would go here, I think. Roughly. I think that's about 45. I mean, I might be wrong. You know, that might be a terrible estimate. But I'm thinking, oh, that could plausibly be that angle, which is half a right angle. You see what I'm doing? Or trying to, anyway.
Yeah.
I'm saying if that's the whole right angle, then that would be about half it. So I'm just saying it's a good idea to get used to trying to judge angles roughly relative to these basic ones.
Okay.
So it's slightly, but not a great deal more than 45, we think, probably.
Okay. So like 47?
About 50, probably, yeah.
Okay.
Also, we might say to ourselves, oh, in that case, could it be as much as 60? And then try and make an equilateral triangle out of that. Is that wide enough to be the corner of an equilateral? If I draw the third side there? Because I've made it roughly isosceles, haven't I?
Yeah.
Is it large enough to be 60?
No.
It hasn't opened far enough, has it, to be the corner of an equilateral? It's left these angles greater, visibly greater than that one. Even though I've drawn the arcs smaller, you can see that they're open wider slightly than this one here. Not much. Don't worry if you don't agree with me there. But you can sort of see that the line I drew here is rather smaller than these two, isn't it? And that would mean that this angle had to be smaller. Because the smaller I make that side, it's going to pull that angle smaller, isn't it? Okay, so probably about 50 degrees or so. That's just by the by. Right, where were we? Right, we're just talking about a general rule which is incredibly important about circles, which is that usually, I mean, what they expect you to write here, they expect you to write opposite, or what was the posher version of opposite? What's the word we put before it?
Vertically, wasn't it?
Well done. Because they're opposite the vertex here. Yes, right. And what they're expecting you to write either on the diagram, which is fine, you know, connected by a couple of arrows. You could point to the two angles and just say, not opposite this time, but angles in the same segment. And we'll discuss how that means anything in a minute. Or the other version is angles on a chord. Oh my God, is it chord or chord? I think it's with an H, like in music.
CH.
Yeah, thanks. You've seen that in maths, I mean, not just music.
Yeah. No, in maths, actually.
Good. I mean, I think you're right. Yeah. Now, what's a chord on a circle?
Isn't it when it's like a kind of like a semicircle, that kind of bit? Oh no, it's
not necessarily then.
The line that, oh, I can't remember. It's like I remember it, but I just can't.
Yeah, you can examples, but you know, you're not quite sure what you know, what are the best examples, or which ones, you know, how to find more or reject some. And basically a chord is, well, this drawing here, before I came along and made a mess of it, it had 4 chords. And these are just all of the straight lines, are chords of this circle, because both ends of all of these line segments are on the circle. That's all a chord is. What does angles on a chord mean? It means this one, it means angles on the same chord. We just drop the word same. Now, why don't we drop the word same here and say angles in a segment? We might have done, but it does have a kind of a use. But then why did we do it here? Yeah. Anyway, because what this means is really is angles on the same side of a chord. Okay. But angles where the two, so here's a chord. These 2 angles here are both on, in this sense, the chord AD. And in this sense, they're in the what's called the major segment of AD. The part of the circle, the larger part of the circle, which AD is dividing into 2 parts. You're thoroughly lost now. You ought to be with the way I'm just, it's terrible.
No, it's okay. Keep going.
But no, really, it's terrible. Sorry, look how messy it's getting as well. Anyway, but good. Anyway, thank you for staying with me though. And so you're allowed to say that, or you're allowed to say that for these 2 angles. And then those 2 angles too, but they will have another reason. If we've shown that this angle is the same as that angle, and then that angle is the same as that angle, the reason being for these that they're angles on a chord, which is to say, as we showed, let's do that again though. It's so important to try and imagine this happening in your mind's eye. Because after all, when we were discussing rotational symmetry here, you did stuff with a kind of mental animation, didn't you?
Yeah.
You imagined making an animation.
Yeah.
And an awful lot of geometry is like that. And they're really testing you on that kind of skill rather than the formal statement of it. Just seeing that, and remembering, and that is a rule, that angle just doesn't change at all as it migrates along the circumference. You don't try and prove it. We just take that as basic in geometry, a basic fact. A circle fact. You've heard of circle facts, probably.
Yeah.
Yeah. Okay, so having said these 2 are equal for some reason or other, these 2 are equal for some reason or other, these 2 are also equal for the same reason as these 2, but of course these 2 are on which chord?
AD?
No, careful. In the sense of angles on a chord, remember we said that this angle, all of this, oh, I never answered your question. What's the rotational symmetry of a circle?
Yeah. Are you asking me?
Sorry?
Oh, I don't know. Infinite, I guess.
Exactly. Well done.
Okay.
And similarly here, we've got an infinite number of angles along this curve, haven't we? And they're all equal to each other.
Yeah.
But these are all angles on what chord?
On the same, on
all of these angles where I'm pointing with the mouse in order to drag this along the curve, these are all angles kind of fixed relative to what chord of the circle?
Really don't know.
The point is they're all pinned down by A and D, aren't they?
Oh, right. Okay, yeah.
What's the old-fashioned word for that? Oh my God. Angles, not circumscribed, not circumvented. Angles not inscribed. Oh my God, I can't remember the old-fashioned word. It's not that old-fashioned either. It'll come to me in a minute. I hope. Angles. Oh, shame. Anyway, but the more modern way, which is meant to be simpler to remember, I've forgotten the other one, is on a chord, or in the same segment relative to that chord. But you mustn't be looking at this angle over here and not be aware that all these angles are only equal because they're both pinned down at A and D.
Yeah.
So these angles over this side are on which chord? If you follow the angles out to where they're pinned down.
AC?
This one here?
Like, I don't know.
See, what's the chord for these angles?
AD.
Yes. In other words, as you follow, you take any angle and you look to the other end of each line. There's A at the end of one line and D at the end of the other leg of the angle.
Yep.
Well, let's do that for these two angles, either one of them.
Mm-hmm.
Can you follow as far as you can go? Oh,
would they be on BC?
Yes, they are.
Okay.
See? And then you want to, oh damn, high controls. I mean, let's do that. So now as I drag this one along the circle, can you see, does that confirm what you were just beginning to see?
Yeah,
in mind's eye?
Mm-hmm.
So they're pinned at B and C. Oh, what's the technical term for the pinning? Angles. Angles. Oh, right. Anyway, there we are. But there would be another reason. We wouldn't have to use that reason again to show that these two angles were equal. We could use a different reason.
Mm.
Can you think of a different reason why we would know this angle must be the same as that one?
No, I really can't.
Well, we've shown that that angle is equal to that one, haven't we?
Yeah.
Because they're opposite. And then we've shown that this angle is equal to this angle.
Yeah.
So do you agree that this angle plus that angle must be equal to this angle plus that angle?
Yes.
And then?
And then?
If you know two angles of a triangle.
Yeah.
What can you find?
The third.
The third angle?
Yeah.
And since any triangle, the angles have to add up to?
180.
Did you say 180?
80.
80? Yeah, quite.
Mm-hmm.
Well, if the sum of those two is the sum of those two, then what's left out of 180 must be the same here as it is here.
Yes. Yeah.
Oh, I see. I can have several of these open. How did I manage that then? Yeah, anyway, I don't know how to work those properly. Right. So finally, but having talked such a lot about one topic, I think we probably ought to, for a change, see if we've got more examples in this book to choose from.
Yeah.
Although, here we are. Woohoo! At last. Hurrah. So let's go to the end of this section. I mean, it says exam style questions on one particular little subtopic, I think. Angles in circles 1. Well, subtended. Oh! An angle subtended. Oh, they're calling it an arc, subtended by an arc. It had been fashionable to say what I said, angles on a chord. I better amend my notes here. Angles on an arc, or subtended by, even better, now that, how terrible, I couldn't remember that word. Angles on or subtended by two, it used to say just 2 points, and now they're saying a chord, and now they're saying an arc, but basically fixed at 2, subtended at 2 points. Angles subtended by the same points, basically. Leave that like that. Are equal, that's what we've been discussing, okay? And now, related to that, it's easy enough to take on board, probably, that basically, right, to use the same example, because you've been thinking, I know it's messy, but you've been thinking a lot about these two angles, haven't you? And how they're equal. And let's look at the general case of that. Damn. Okay. No, let's not. It's too messy. And I was going to use E. Just so dim for me. Right. Pardon me. Right, I'll go new sheet. So here's a circle. And here's 2 points again. So those would be A and D probably. Were they called A and D? I'm not sure.
Yeah.
Now, let's pin an angle down or subtend it at those 2 points, right? So these are all the angles that I'm making, this infinite number of angles, but they're all equal because they're all subtended by the same points or at the same arc or the same chord. The chord would be a straight line joining those 2 points. A chord is any, I never made that clear, sorry. A chord is any straight line from one point on a circle to another point. But then any straight line like that is going to divide the circle into 2 parts, isn't it? And those 2 parts are called segments, and the bigger one is called the major segment, and the minor one is called, well, you know what I mean, the smaller one. Yeah. Now, so this chapter of the book is talking about the fact that all of these angles are equal, right?
Yeah.
And then this chapter of the book is also adding a second rule and saying that, now can I make a second path, please? Because if I don't want to do that, do I? Yes, I do. Oh, good. All right, it worked. So if I go there, oh no, hang on. Well, if I take that one there, and then, oh, all right, have it that way. Put that one there. Can you see these?
Yeah.
Now, this one, I'm not going to drag anywhere. I'm going to leave it where it belongs in the dead center of the circle. Okay, that one's not moving. But a very interesting fact about circles is the relationship between all of these at this side, that angle there, wherever it is, because it doesn't change, does it?
No.
At all. The relationship between this angle here and this angle at the center, subtended by the same 2 points. Can you guess what this relationship might be? Which one's bigger?
What that angle.
I can't see which one you mean by that, because
I meant the one your mouse was on. So the one in the middle?
Describe it, even the one in the middle, yes, the one at the center. And this is how we would describe it, the angle at the center, and we wouldn't bother, you would be implicit probably. Well, we'll see how the book describes it in a minute, but the angle at the center, now is that larger or smaller than the angle on the circumference?
I think it's larger.
It's larger. Can you guess, perhaps, how much larger? Let's take a particular example. I mean, we've virtually got it, actually, haven't we? This angle here is probably what? Roughly.
45? No. 80 degrees.
Okay, I mean, yeah, in the right zone, but I'm surprised you aren't tempted to think that that might be what special angle?
90.
It is, isn't it?
A
Could
right
be
angle,
the corner of a square, just about. I mean, not perfectly, maybe it's a bit smaller. Okay, and now let's take the particular example of this one on the circle, on the circumference, where they join there. Now, what does the angle on the circumference look like roughly?
60 degrees?
As big as 60?
No.
Sorry,
no.
I mean, I'm looking at this.
Yeah.
And thinking, what looks special about that triangle?
It's right angle.
Where's the right angle?
In the center.
Here. It's got a right angle there. And what else is special about this triangle? Possibly. I mean, doesn't it look a bit symmetrical?
Yes, yeah.
About that mirror line there?
It does. So would that angle be 45 degrees?
Yes, and it could be. I mean, if it's hard to see, spend some time trying to see it. Imagine a line that's tangent, as we say, to the circle. You know that word tangent? Do you? Do you know that word tangent?
Yeah.
What's
like the line that, what you're drawing, like
that one there.
Yeah.
How am I having to try to draw it if it's tangent?
And it goes like just touches the circumference of the circle.
How many times? How many times does it touch the circumference?
Once.
Once only, if it's tangent.
Yeah.
Whereas if it's just any old line, it'll be a chord of the circle for a start, an extension of a chord on the circle, or it'll touch it not at all. But if it touches it just once, that's an important circle feature, isn't it? Where the tangent. Now, what what's the basic fact about tangents to a circle?
Not sure.
Ah, right. Do that as well. I think I'm going to lose those paths now. That's the trouble. Damn. But anyway, circle. Well, no, let's do it here. So tangent. Ah, it's not a tangent yet, is it? Because it's touching in two places. But if we can make it touch in one place only, then it's tangent. And then if I stroke that, right. Now, a basic fact about tangents, which is so important, is that the angle it makes with the radius where it touches. Because of course, if it touches there, there's going to be a straight line going from there to the center of the circle. And what would we call this straight line going from here to the center of the circle?
The radius.
Yes. And the basic fact about tangents is the angle between the radius and the tangent is
180. Oh, or 90.
90 between there and there. I think what was happening there is you were going from there and going all the way around. But when we say the angle between two lines where they meet, we're just looking at part of the lines, yeah?
Mm-hmm.
So yes, tangent, radius, therefore angle. You're going to use that quite a lot in the circle work you do in maths.
Okay.
Okay. Now, given that that's true, that's why I was thinking if you notice that, then you might be able to start judging, as I was trying to sort of more or less rightly influence you to judge that, well, maybe that point is a bit better over there. From, no, what was it? Where was I doing it? Yeah. Okay, so that's, you see, we thought that this was a right angle here. And then I was hoping that you might agree. Damn. This is what I don't understand. Why? How can I tell it that I finished? Damn.
Oh.
Control Z. What would we do without Control Z? Finally.
There we go.
So I was hoping that you might be willing to imagine. So that center's not very centered, is it? Well, if I were to take that round a bit, oh, I don't know. But you might be willing to believe that while this looked as though it was roughly a right angle, this looks as though it's roughly half of a right angle.
Yeah.
Because
yeah.
Here's your isosceles right angle triangle again. The right angle's here at the center. And then these must be both 45. But look, yes, it could be half of that right angle there. Yeah. So this is all about noticing what's going on and starting to imagine. I suppose there ought to be more actual drawing. Until people start actually drawing with a pencil and set squares and compasses and stuff, they won't be noticing these relationships. Anyway, here's a right angle, here's half of a right angle. But then if that's 45 degrees, what's happening as we move the angle along the circle? What's this angle now, do you expect?
Wouldn't it be the same?
Yes. Because it's still subtended, pinned down at the same 2 points. Ah, but then surely that means that the angle, what's the relation always then between the angle at the center, subtended by 2 points, and the angle at the circumference, subtended by the same 2 points?
They always stay the same?
They both do stay the same, but what was the relationship between this one and that one? In this particular case, what's the relationship between this right angle and this 45-degree angle? How do they compare?
I don't know.
And here it is happening again.
Yes.
45, you can see like that's half of a square we're making here.
Yeah.
And here we've got a 90-degree angle. So here's 45.
Yeah. Oh, okay. So
Well, hang on, let's imagine widening these 2 points. Now, this one's still remaining constant as I move it along. Can you guess what the relationship is between this angle at the circumference and this angle at the center?
But they're both.
Well, when this one was 90 at the center, when the angle at the center was 90, what was the angle at the circumference?
It was 45, wasn't it?
Yeah. Well, could the relationship be, which is kept the same even when the center is no longer 90, neither is the angle at the circumference? Can you guess what the relationship is between the angle at the center and the angle at the circumference?
I really can't.
Well, when one of them is 90 and the other is 45,
Yeah.
what's that relationship?
One is half of the other.
Yes.
Yeah.
What about here? What do you reckon the angle at the center is? Roughly.
Oh gosh.
Difficult one. Yes, it is an oh gosh.
On
On the other hand, what do you reckon this is? Couldn't that be a
40?
60 set square?
Oh, yeah. Oh my gosh, yeah. Yeah.
Very roughly. In which case this angle is, sorry, in which case this angle is what?
45?
Ouch. I thought this was a 30-60 set square.
Oh, okay, so that would be, was that 30? No, that was 60. That was 60.
Double that one, which is 30, because it's half of an equal angle, notice.
Okay, yeah.
Okay, if that's 60, what's this? The angle at the center of this configuration here.
120?
Yes.
Yeah.
Okay. Can you guess what this angle is, roughly?
60-ish?
Yes. Yes. Yeah. When the angle at the center was 90, the angle at the circumference was?
Half. Well.
Yes, 45. When the angle at the center is 120, the angle at the circumference is?
60.
So this second rule about triangles is this comparison between any angle subtended between 2 points, any angles on a chord or an arc, which are equal to each other, but they're also half of the corresponding angle at the center, which is not going to move as this angle moves.
Yeah.
That stays constant. The angle at the center has to stay at the center.
Yeah.
So that's what they're talking about here.
Okay.
Where? This one here, key point. Do you see their little diagram?
Yeah.
X and 2x. Do you see where they're saying x and 2x? Oh, hang on.
Mm.
A bit bigger now. It's a bit of a cramped diagram with a big O in the middle there.
Oh right, yeah.
But do you see how they're labeling the angles? They're saying X, whatever it is, and then the corresponding angle at the center is 2x.
Yeah. Okay.
Let's see what they're saying. The angle at the center of a circle. Theorem, big posh word for fact. Theorem, the angle at the center of a circle is twice the angle at the circumference when they're both subtended by the same arc. I thought subtended had gone out of fashion, even though, you know, to the extent that I'd forgotten the word. I'm glad the dumbing down has reversed, and we're so subtended is just referring to the points A and B. All right. So we didn't get a chance to practice those. We could do that another time if you want to, or we could do something completely different if you've had it with circles now for a while. But the point is, once you get some, it would be worth persevering with, because once you get some practice at circles, it's such fun, honestly, if it's a topic that you're not afraid of. You brought it up, so perhaps you've been having, as yet, a difficult time with it. I don't know.
Yeah, I don't really get angles that much.
Right. I mean, you may need practice just judging and estimating them for a start, relative to the basic ones. 30 and 60. Next time you look at the clock face, is what we'll talk about next time. I'll leave it till then. Sorry, I've kept you too long. But
That's okay.
you know, whenever you look at a clock face, look for all the lovely equilateral triangles sitting in it.
Okay, I will.
Between 1 o'clock, 3 o'clock, 5 o'clock, 7 o'clock, 9 o'clock, and 11 o'clock, for example. Can't write.
Okay.
All right.
Okay. Well, thank you.
Have a good week. Cheers.
See you next week. Bye.